Hello students, this is Dr. Munir Omar with CS 371 Data Communication and Networks. Today in lecture number 32, we will be studying about the error detection. We have already studied about the impairments in which we studied that the transmitted data may get corrupted during the transmission, and it is possible that the received data would not be similar to the transmitted. So the corrupted data is caused by the corrupted bits, and we refer such scenario as error in the received bits. So in today's lecture, we will study about the detection of such corrupted or changed bits. By the end of this lecture, you would be able to understand the basic concept of an error in computer networks and its types. By computer networks, I mean the data communication or the transmission of data from one host to another. In this lecture, I will explain different type of error detection codes and how does error detection take place in data communication. I will also discuss few well-known error detection techniques in details. These are the contents for our today's lecture. First, we will define the error and its types. In this lecture, we will define the two types of errors. Then we will discuss the process of error detection. We use redundant bits for the detection of errors. Then we have some methods for detecting errors. These are vertical redundancy check, then longitudinal redundancy check. These two use parity bit mechanism. So we will also study about the parity bit. Then we have cyclical redundancy check. We can also call it cyclic redundancy check, CRC. And at the end, we will have the checksum. We will look into all these detection mechanisms, and we will have some examples for these. Okay, let's start with error. Whenever a message is transmitted, it may get scrambled by noise or data may get corrupted. If the transmitted bits are changed or lost, then we can say that that transmitted data got corrupted. Data can be corrupted during transmission. This is obvious because the transmission medium is not perfect. So any type of data can be corrupted. For reliable communication, errors must be detected and corrected. This is the need of data communication, that the errors must be detected and corrected. Error detection and correction can be implemented at Datalink Layer and Transport Layer. Data can be corrupted during transmission. Most of the applications require that errors be detected and corrected. There are two types of errors: single bit error and burst error. Single bit error. In a data frame, there is only one bit which is corrupted. This one bit can be anywhere in the data. So here we have 8 bits transmitted, and this 0 got changed, and the received 8 bits are different. Here we have 1 instead of 0. So this 1 bit is changed, and this error is 1 bit error. In a single bit error, only 1 bit in the data unit has changed. Then we have burst error. Data frame is received with more than 1 bits in the corrupted state. Errors do not occur in consecutive bits. The length of the burst measured from the first corrupted bit to the last corrupted bit. So first thing, there might be more than one bits. Here, if we look into these bits are sent and these are received. So some of the received bits are different from the sent bits. These are actually corrupted bits. So these are more than one. Second thing is that there isn't any condition of consecutive bits. Now, if we look into these two bits, these are consecutive, but the burst is known for non-consecutive multiple bits. Third thing is the length. The length is measured from the start till the end, from the first corrupted bit till the last corrupted bit. So this is the length, and this length is equal to 8 bits. A burst error means that two or more bits in the data unit have changed. Then we have error detection. We use error detecting codes, which are additional data added to a given digital message. If we are sending data, then for error detection, we also add some additional data, and that is also transmitted with the original data. The additional data helps us detect if an error occurred during transmission of the message. To detect or correct errors, we need to send extra bits with data. These extra bits are also called redundant bits. Error detection with redundancy. The simplest way is to have two copies of data unit. For sending, we have two copies and we send both the copies. At receiving side, these both copies are compared. If both are equal, means that there is no error. This is the simplest way. But if we apply this thing or implement this thing, what will happen? It will double the transmission time, and also the computational time will be slower. So for redundancy, only extra information is added, and this information is less than the actual data. Shorter group of bits may be added to each packet, and these additional bits are received by the receiving device, and if the receiving device detects an error, then it discards the received packet, and if it detects that there is no error, then the data is accepted and the additional bits, the redundant bits, are discarded. So this diagram shows the process of adding redundant bits and then redundancy check on the receiving side. First, data is taken, then a function is applied on the data, and some redundant bits are appended with the data. So the sender was supposed to send this data, but it sends this entire block, which is composed of actual data and the redundant data, which is generated by a function. At receiving side, the receiver apply the similar function, and if there is no error in the data as per the process, then accept the data, and if there is an error, then that data is rejected by the receiver. There are four types of redundancy checks. The first one is vertical redundancy check, VRC. The second one is LRC, longitudinal redundancy check. Then we have CRC, cyclical redundancy check, and the last one is checksum. So we will study all these in the coming slides. Parity bit. One additional bit is added with the actual data to make the number of ones even or odd. So we will have even parity or odd parity. The additional bit would be called as parity bit. So for redundancy check, we use parity bit. The parity bit can be set to 0 and 1 depending on the type of parity required. Let's say for this example, we need even parity. So here we have 1, 2, 3, 4, 5. 5 ones. So we must make these ones as even. So here we should provide 1 as an additional bit. Now here we would have even number of ones for even parity, and if we need odd parity, in that case we must provide 0 here so that the number of ones in this entire block data plus parity bit must be odd. The first redundancy check in our list is VRC. VRC uses the parity bit. It is the most common and least expensive mechanism for error detection. As we know, in parity bit, a redundant bit called parity bit is appended to every data unit so that the number of ones in the data unit becomes even or odd. So, for adjusting the even and odd number of ones, we set the value of parity bit to 0 or 1, as we did here by providing 0 or 1 to make the number of ones even or odd. Now here we have data, and this one bit is appended with this data to make the number of ones as even, because we need even parity and the function is used even parity generator. So here this additional one is VRC, and this block is data. This entire block data plus parity bit is transmitted to the receiver, and at the receiving end the receiver counts the number of ones, and if these are even, then the data is accepted, otherwise the data is rejected. So this VRC can detect only one bit error. The VRC is designed to detect all single bit errors. However, it can detect 1 bit error, 3 bit error, 5 bit error, or we can say that odd number of bits that are changed can be detected by VRC. It cannot detect errors where the total number of bits changed is even. Then we have longitudinal redundancy check LRC. Parity check bits are calculated for each row, which is equivalent to simple parity check bit. This is actually two-dimensional parity redundancy check, and in this check we take multiple bytes and calculate their parities under those bytes. Parity check bits are also calculated for all columns. Then both are sent along with the data. At the receiving end, these are compared with the parity bits calculated on the received data, and the result is concluded. This one is also known as two-dimensional parity redundancy check. So here let me show you this example. So here, if you look into this data is supposed to be sent by the sender. So there are 4 bytes. So what happens for each column in these 4 bytes, or we can say for each bit in these bytes, we calculate a parity. So for first bit in each byte, we are calculating one parity. Here we need even parity. So this one is actually odd. The number of ones is odd. So we must add 1 here. Here again, this one is odd. So make it even. This one is already even. So no need to provide 1. So we are giving 0. Similarly, ones and zeros are given to all the columns. So this data plus the calculated parity bits are sent, and at the receiving side the same process is adopted and checked whether there is any error or corruption in these received bits. Here we have one another example. We have 4 bytes. These 4 bytes are taken, and for each column in these 4 bytes, we calculate a parity bit, and we make even or odd parity. So here we have odd number of ones, sorry, even number of ones. So 0 is given, here only 1 is present. So odd number of ones, 1 is given to make it even. Similarly, zeros and ones are given. So this one is actually the LRC, and this LRC is appended with this actual data, and it is transmitted. So the original data plus LRC is transmitted, and at the receiving end, the receiving device calculates the even or odd numbers according to these blocks and these parity bits and conclude a result. Then we have cyclic redundancy check, CRC. CRC is performed at Datalink Layer.